Good. Okay, so I'm going to be talking about some specific options and steps you can go through with the Intel compiler, because now the Intel compilers are Intel have a complete compiler suite, Fortran, C and C++ compilers, and it's in their interest to help people to vectorize their code using their compilers. And they provide a lot of tools that we can use to achieve this. So in my talk today, I'm just going to go through just a few of the more common options that should cover about 95% of your use cases. So first of all, I'll just give a little introduction to using the Intel compiler, then look at in more detail at vectorization reports. So Neil showed you a brief overview of vectorization reports from the Intel compiler. I'll go into some more detail. Then we'll look at our guided optimization, which is another compiler tool that can be very useful for finding more complicated dependencies and problems in your loops that stop the compiler from vectorizing. Then we'll look at some directives you can add to your code. I think Neil later on will also be talking about some directives that are more generic. And then I'll also talk about Intel Silk. I don't know if I'll talk about that now. I might talk about that later. But those are some extensions that Intel has made to the language, to C and C++, that will be very familiar to Fortran and MATLAB users that are very nice. Now, before I start, I've just going to point out that I'm just looking at a very small subset of the tools that Intel make available, and they've got a lot of documentation for these online. So I've just given you some links. The links were very long, so I had to shorten them. Now these slides are in the directory for the workshop, so you can go to these sites here, and you can get some more in detail documentation. The first two guides are guides specifically for x86 Intel processors, like our Sandy Bridge. And this is a guide that is all about developing software for the Xeon Phi, which, how many people here have heard about the new Xeon Phi processors? So these are, yeah, you've heard about it. So these are some new processors that are released by Intel that have got many. Yeah, Knight's Corner. Yeah. Yes, yes, yeah. Yep. So they've got about 60 cores, but the tools, the techniques that they discuss in this tutorial are actually equally applicable to Sandy Bridge. And if you actually write code for Sandy Bridge using the techniques in here, you will find that your code performs well on both Sandy Bridge and Knight's Corner. So just to start off with, we saw before in the tutorial exercise that the Intel compiler will automatically vectorize with O2 or O3. If you don't want to have vectorization, you can compile at O1 optimization level, or you can pass O2 no vec. And this might actually be useful if you're trying to investigate your code and see whether or not you're actually getting any speed up from vectorization. It can be very useful to turn the vectorization off to see what difference that makes. And another thing is that on the Sandy Bridge processors, like those on Pilatus, these use AVX registers, which are 256 bits wide, and that means they can store 4 double precision numbers or 8 floating single precision numbers, which is, but by default, the Intel compiler will not target those. It will instead generate code for 128-bit SSE instructions. So you have to pass an additional flag, -x AVX, if you want to compile for AVX. And on the GNU compiler, it's a very similar flag. GNU similarly doesn't compile for AVX unless explicitly asked to. And there's also the X host flag if you're uncertain about your target machine, but if you know that you're going to be running on the machine that you're compiling on, you can use the -x host flag. Although you should be very careful about doing that for the systems at CSCS, because sometimes the processor on the login node will be different from the processors on the compute node, so you can get some problems there. So here's just an example of calling the Intel C++ compiler, which is ICPC instead of ICC, and generating code that has AVX instructions. So the first step is, generally what we do is we sit down and we plan how we're going to write our code so that we take advantage of vectorization. And we think we've got it figured out, and then you implement your code, and then you think that's going to vectorize for certain. But compilers are very, very conservative. Compilers prioritize getting the correct answer over over performance. And quite often, there could be a reason why the compiler can look at your code. It'll decide that it can't say for certain whether or not using vectorization or parallelization won't introduce bugs or inconsistent results to your program. So it will often not vectorize. So we should always, you get a report from the compiler asking it explicitly, did we manage to vectorize? And with the Intel compiler, we use the -vec report flag followed by a number. So the number is in the range of 1 to 6, and depending on that value, you will get more or less information. So here's an example, like we saw earlier, of compiling with our vec report level 2 on some code, and you can see there's quite a few different messages that can be generated. And really, when we look at a report like this, the ones that we're interested in are the loops that don't vectorize. And of these, often you will, I don't know if you saw in the last exercise that it might comment, it might say, oh, this loop didn't vectorize because it was an outer loop or it wasn't an inner loop. And those generally we don't worry about. But this here was an example we saw before, and this is something we should look at. So the vectorization report takes an argument from 1 to 6, which will generate different levels of information. Level 1 just tells you which loops were vectorized, which is, it's nice to know, but it's not most interesting. What's most interesting is finding out where we have problems or loops that didn't vectorize. So level 2 tells you what was vectorized and what wasn't vectorized and gives you a simple reason, like, for example, telling you that there's a dependency. Level 3 will do the same, but where there has been a problem due to dependency, it will give you some more detailed information that might help you find the cause of the problem. And then 4 and 5 show us just the loops that haven't been vectorized. And then level 6 gives some more detailed comments, as we'll see over here. So here is, I just had a simple little bit of code, and I compiled it with the different reporting levels, and this is the output I got. So first of all, vec report 1, if you just saw that, you'd think, oh, you're doing pretty well. But what we're interested in is vec report 2, where we say, oh, only one of the loops is vectorized, and then we've got two different messages here. One saying that we have existence of a vector dependence, and the other one saying that this one here says that the compiler has had a look at the loop and figures that it's possible to vectorize it, but it's probably not worthwhile. And we'll see an example of that later on. And then vec report level 3 gives a bit more information about this dependence here. So it tells us we have assumed flow dependence between line 20 and line 20. Now, some of these comments that you get out of both the Intel and the GNU vectorization and optimization reports were written by computer scientists, and they're very difficult to understand. So I'll show some. Sometimes it's very simple to see what the problem is, but sometimes it's more complicated. And I'll show some other tools we can use to try and understand what this means later on. And now, here we go. So this is the loop that caused this problem here, the existence of the vector dependence, and we saw just this example in the little exercise we did before. And in this case, we've got a very short loop. So this theoretically would vectorize nicely. However, the compiler has said the loop is only 4 elements long, so there would be potentially very little benefit in vectorizing that. So here we've got an example of a slightly more complicated loop. So it's embedded in a function here that we have an array of doubles of length n. And we loop over the array, and if the entry in the array is less than or equal to 0, we set this this value t to be equal to I, and then if the value in A is less than 0, we do something using the value of t. And the compiler doesn't like this. It tells us, it wasn't vectorized because there's a vector dependence, and then it gives us this message here, which maybe by looking at this loop you can tell what's wrong, or after thinking about it you can tell what's wrong, but really this message doesn't, well, to me at least, it doesn't say very much. I don't know, Neil, does that mean anything to you? Sorry. And that's actually more information than the GNU compiler will give you sometimes. So there's another tool that is provided by Intel, which you can activate by passing in this flag, and this is called the guided auto parallelization tool. And this tool is it reports on many different issues that it encounters that stop it from optimizing your code. So not just our vectorization, but it can also try to automatically parallelize your code and report on potential issues there. And that's actually a very useful tool to pass over a loop that you're planning to parallelize using OpenMP. And I think that's actually a very good first step to do. And but it can also provide some more useful feedback for some of the more complicated loop dependency problems. So this is the report that it gives for that example that we saw before, and it says it basically tells you what to do. You might want to assign a value to the variable t at the beginning of the body of the loop on line 14. This will allow it to be vectorized. And if we go back here, we see, well, the value of t is only set when the value in A is less than or equal to 0. And the value in A is then only modified if its value is less than 0. So in fact, this value will always be set. If this condition is true, then this condition is also true. So this value will actually only be set when we... this value here will only be set when this condition is true. So we can modify the code like this. We can just set t equals to I, and then if the value here is greater than or equal to 0, then this will just get ignored. And as a result, when we recompile after making our little change, we get the result we were looking for. So it doesn't work for all loops. It doesn't, so for some of the simpler cases, like the ones you looked at in the last exercise, it won't give any feedback. But for those ones, hopefully you should be able to fix them just by looking at them and using the vectorization report. Now, it can also help with the automatic parallelization, and the Intel compiler has an additional flag you can use to automatically parallelize your code. So this is a little bit off topic on the vectorization that we're talking about today. It's something that might be more interesting tomorrow. But this is something I was playing around with last night. And what I found was something that's a very useful example of what can go wrong when you try to just rely on these compiler reports. So I then took the fixed code here and then tried to get it to automatically parallelize. And it told me this. It said you might want to set pragma loop count min 256. What that means is if I say that, that's telling the compiler that I guarantee that this loop is going to loop around at least 256 times. So n will be at least 256. Because if the loop is less than that, there's the overhead of initializing the threading won't justify the effort of the speed up you get from the parallelization. So I added this I added this line and then recompiled, and the problem went away. And you might assume that the problem, that you've solved the problem and that the loop has been parallelized. But then there's one last step you can take when you want to really get very detailed information about optimization, and that's to get a full optimization report. And this takes the flag opt report, so just like vec report, but opt report, and it will report on all of the different steps that the compiler takes when optimizing. And this actually, all of the things you see in the vectorization report, they also appear in this report. And unfortunately, you get a lot of information in here, and it really is. A lot of it is very cryptic, and the documentation is very hard to understand, or there just isn't any documentation. But if you know what you're looking for, you can find some interesting information. So I got the optimization report, and this is just a little bit that I cut out of the optimization report. And it tells me that we're in the main function of the program. So in every C or C++ program, we have a main function. And from the main function, I called this function trouble. So you see the function was called trouble, which is a good name. And you can see it's telling me that it has inlined this function, and then it tells me that it did not parallelize it, despite the fact that I had followed all of its instructions, and the guide report said that everything was fine. And this is because, and then later on in the report, further down, it then also compiled this function independently, and there it said it had parallelized the code. So when I looked into this in more detail, I found that when it said 256 iterations, it didn't mean n had to be 256. It meant 256 vectorized operations, which for our AVX means you have to have a loop trip count of at least 1,024, because you will do, in each iteration, you will do 4 operations. So by increasing n to 1,024, this finally parallelized. So this just shows that even though you've got to be really careful that you're actually getting what you think you're getting when you use these compiler reports. And if you're not seeing the performance that you think you should see, to try and dig a little bit deeper. And these optimization reports are the last spot you can go digging, and in there you'll find a lot of information. So directives, I don't know, Neil, do you want to speak about directives first, or should I go through these? So often, the directives are something that we can put into our code. This is both in Fortran, C, and C++, and the directives are all very similar, just slightly different syntax in each of the programming languages. And we can give the compiler hints. So it might, for loops where the vectorization report says that the compiler isn't sure about this, so it's not going to vectorize, we can then give it hints or suggestions that will tell it that it's possible to vectorize the loops. So some of the directives that I'll go through here are unique to the Intel compilers, so they're not available in other compilers. And some of the directives are more standardized across all or most of the compilers. And as we'll see, some directives are stronger than others. So some directives, the compiler will still look at what you've told it and then say, no, I'm still not going to vectorize. And other directives, you can force the compiler to vectorize no matter what. And you can end up with a lot of problems if you do that, because you might actually end up producing the wrong answers. So I recommend, if you've got a choice between 2 different suggestions, here are a couple of them, IVDEP and SIMD, choose the one that is the least forceful, that is the least forceful, to avoid any potential problems. So the simplest one is pragma IVDEP, and we use this when the compiler says that there's some sort of vector dependence. Now this wouldn't work for the example we saw before, the xi is equal to xi minus 1. Because that sort of vector dependence is very difficult to work around. But in more complicated loops and more complicated data access patterns, you can quite often get where the compiler will not be certain that it can, will not be certain that vectorizing won't lead to some sort of vector dependencies. So you can insert a pragma IV dep. So for example, here's a loop, and by doing this, pasting the pragma IV dep here, we're telling the compiler that the memory regions pointed to by A and B do not overlap, so there's no problem in vectorizing. Now, another way of doing this is to declare A and B as restrict pointers in C and C++. Has anyone heard of restrict pointers? Okay, Neil? Okay. So yeah, you'll often see restrict pointers, particularly in all the documentation. It says just put a restrict keyword in there, and that'll tell the compiler that it doesn't have to worry about these dependencies. But I find that in practice, actually, the compiler will often completely ignore those. They're not properly implemented, but the compiler will pay attention to this, and you can get very good speed up, particularly for the Intel compiler with this. But the pragma IV dep is something that's it's a very almost a standardized, almost a standard. It's available in the Intel, the GNU, and the Cray, and also PGI. Do you know, Neil? Probably, maybe. This one, pragma vector always, I think, is unique to the Intel compiler, and you can use it just to tell when the compiler is uncertain about whether or not it would be worthwhile vectorizing a loop. So this is our example from before, where we have a very short loop, and the compiler comes back and says it didn't vectorize this because the loop is too short to justify that. Now, in this simple case, there really is no reason to vectorize this loop. But in other cases, it might actually be worthwhile getting the compiler to vectorize. So then you would just stick a pragma vector always in, and it will vectorize this loop. Now, pragma SIMD is a recent addition to the Intel compiler, and this is a very powerful directive. It tells the compiler to really go out of its way to do vectorization. As a result of doing this, you can have some unintended side effects, and you have to understand that you're telling the compiler to do something that it is not certain about. And you have to take responsibility if things go wrong. And that means that if you are going to go forcing the compiler to parallelize using the SIMD, you should very carefully validate your results and guarantee that you actually get the correct answer when you use this approach. Now, it's currently implemented by Intel only. It's been recently introduced, but I saw in the documentation that was just released for the proposed standard for OpenMP4 that this is going to be, or some subset of the pragma SIMD will be introduced to the OpenMP4 standard. But unfortunately, the way these things, the speed at which the standards committee for things like OpenMP move, who knows when that will actually become available. And here are some examples of how to use pragma SIMD. There are lots of other different ways you can use it. It's actually got a lot. It's a very powerful tool that you've got a lot of different options and a lot of different ways, subtle things you can tell the compiler about optimization. Here are 3 basic examples, but I really do recommend going to the documentation. The PDFs that I referred to at the start of this talk have more detailed documentation. So the basic usage is you just say pragma SIMD, vectorize this code, vectorize this loop at all costs. It has a reduction operation, so you can say here we've got a value x, which is just a single double, or a double, and we're going to calculate the sum of all the entries in A. Now, these sorts of reductions are actually a bit tricky to do in parallel using vector units. So we just give the compiler that a little bit of extra information that we're doing an addition reduction on the variable x. Now, the Intel compiler will actually vectorize this loop just fine without this directive here. However, for more complicated examples, it can very quickly get confused or become uncertain whether or not it should vectorize. And that's when instructions like this become useful. And you can also use it for loop carried dependencies. So this is similar to the example we looked at before, which was something like AI equals some function of AI and AI minus 1. But in this case, we can see that AI is dependent on the value that came 16 times before it in the loop. So there is actually an opportunity to do some vectorization on short vectors of length 16. And you can give this directive to the compiler saying that it should vectorize, but only for short blocks of length 16. So there are lots of other directives. Some useful ones are pragma vector aligned, where you can tell the compiler that the arrays or the pointers you're giving it, or the arrays are aligned. So they're aligned on this will assume they're aligned on a 32-byte boundary, which can allow the compiler to do aligned loads and stores, which are sometimes can be much faster. So it's worth trying that out. But if you do this with information that isn't aligned, you'll usually get a segmentation fault. So you have to really be sure that your data is aligned. There's a pragma vector non-temporal, which tells the compiler that you're not going to be reusing this information. So once it writes the information back to memory, it shouldn't store it in cache. And that means that you'll have more cache available for storing the information that you want, which is again a very good optimizing strategy. And finally, pragma no vector. You just say, for this loop, don't vectorize. And again, this is not particularly useful for, it's not going to make your code any faster, but it's very useful if you want to see whether or not the vectorization is actually having any effect on your loop. Okay, so I might hand back to Neil now. And later on, we'll go into the Intel Silk Plus, which is an extension to the language.